Basically, what transpired prior to the Big Bang, which necessitates caution with the language. Consequently, if you define the Big Bang with extreme caution as the time the universe was extremely dense and hot, likewise, as stated, that cannot be disputed because we can see it from our window. Our preferred explanation for how the universe reached that state is that before that, there was a time referred to as inflation. This question has always been a big difficulty for scientists, but now it appears that they have located the solution. It has shocked scientists like Brian Cox, who revealed that a terrifying event existed prior to the Big Bang. So, is the universe the same as it was, in a sense of being cold, empty, and expanded extremely quickly, and that growth slowed down, came to a halt, and the power that was the expansion's driving force was dumped into space, warmed it up, and produced all the particles from which were made what we refer to as the Big Bang? Why did it exist before the Big Bang? Let's find out. Additionally, that theory has a sort of extension, also known as eternal inflation. It is that the inflation basically disappears for an interminable time before abruptly coming to patches. So you can imagine how far the space-time stretch is, the universe's fabric. After stretching out, it slows down and comes to a complete stop. In every single one of those patches is essentially a massive explosion and a universe that includes our own. So you end up with a picture like this of a universe of infinite fractals, basically a limitless number of Big Bangs, also known as the inflationary concept of the multiverse. In the vast cosmos, it appears to be an absolute nothingness, theoretical, as opposed to actual. Even if all energy was taken out of the universe, it would not be truly empty at the moment. Radiation is everywhere in the universe. Nutrients, dark matter, and antimatter. The universe would not exist at all without energy. It continues to produce new forms of energy in this phenomenon that seems to perplex us. The universe doesn't get our idea of total emptiness. If we removed all energy that leaves a void, one would expect the universe to attain absolute nullity. That is not the case at this time. Its expansion, even in an empty universe, would continue to emit radiation. This extends into the distant past, or even further prior to the violent Big Bang. It appears that the universe never truly becomes void. Given everything, is it conceivable that the universe got its start from nothing? But we can guarantee that something persists always, even when particles, quanta, photons, and antiparticles are removed. If we move the empty space we removed, away from any sources of mass or energy, remove any external electric fields of magnetism and gravitation, and prevent gravitational waves or photons from entering a physical form, this area is still devoid of anything. Quantum fields persist, and fundamental rules and constants of physics last because of an inherent zero that has a finite, positive, and non-zero value. This is a point of energy in that space, representing the closest possible resemblance to nothingness in our universe. You might picture something even worse. Affirm that it lacks physical reality. No experiment can reproduce this kind of condition through scientific principles that we acknowledge, since true nothingness cannot currently coexist in our universe. The reason remains unanswered by science. Currently, our universe appears to be filled with stars and is far from empty. Cosmic rays, gas, dust, galaxies, and quasars, and the radiation that comes from starlight and the relics of the Big Bang. Including better instruments for observation, we could possibly find additional signals we anticipate will be present. This encompasses waves caused by gravity produced by any mass that moves through a dynamic gravitational field, cryptic messages from the constituents of dark matter, and an overall view on both active and dormant black holes, other than the ones emitting the most radiation. This is the cause of everything we see in a universe that is both dynamic and perpetually shifting. From a physical perspective, it is fascinating to comprehend the grand scale of our universe's evolution. The known universe's fabric suggests that space-time is expanding. If 2 points are placed far apart in space-time, the distance that separates those 2 locations and the length of time required for light to travel between them, the wavelength of the light moving from one location to another, all rise over time. The universe is not only expanding but also becoming colder as light expands, moves at longer wavelengths as it stretches toward cooler temperatures and lower energy. Temperatures that made the universe hotter in the past will further deteriorate into the objects from the future during this process. The universe's mass or energy attracts one another to form groups, establishing an extensive cosmic network. If you were to completely eliminate all content, the entire amount of energy that would be radiated would essentially remain empty. You'd still have space itself that continues to expand, governed by the physical laws and still affected by the quantum fields. This is the closest to the entire universe's physical similarity to nothingness, yet it continues to follow specific physical laws applicable to a physicist in this particular scenario. Removing any alternative would result in a state that is unrealistic and no longer reflects the universe in which we live. This hints that dark energy, as we currently comprehend it, would nonetheless be existent in this fictitious universe, essentially meaningless. If every quantum field in the universe was set to its lowest state of energy, we would arrive at the energy of space at the 0 point, where there is no possibility to extract more energy for mechanical activity in a universe that includes a cosmological constant or dark energy. The 0 point energy in quantum fields is conceivable that it wouldn't really be zero. Since the universe continues to grow and cool, eventually, in the distant future, radiation takes over as the main component, exceeding all other types of matter and radiation, leaving behind dark energy as the primary impact. But there is also a period, not in the history of the universe's future, but a long time ago, when something else, in addition to matter and radiation, prevailed during cosmic inflation prior to the Big Bang. The universe changed very quickly with constant growth. Rather than being dominated by radiation and matter, the field had control over the universe's energy of inflation, similar to the current dark energy, but it's much more effective and expanding significantly more rapidly. Assuming that eternal inflation is true, where might the universe have started? It must have been a first step in addressing this thoroughly. Let's decipher 3 frequently misunderstood concepts and discuss each one. The explosive Big Bang in the theory of our universe's relationship to cosmic inflation and its role in preparing for and preceding the Big Bang, and the question of a final beginning of the universe or its source, and why the original inflation and the Big Bang idea may not provide a satisfactory response to this query. At the beginning of the 20th century, a significant synthesis was achieved when 4 key pieces of information came together. A breakthrough in the field by Alexander Friedman demonstrated Einstein's general relativity, that a universe uniformly filled with energy and matter in any form cannot remain the same, but must either grow or restrict. This expansion's rate or contraction is influenced by the overall energy density in space. Henrietta Leavitt's observational work established a relationship between the time period of variable stars' brightness and dimness and their inherent radiance, which is known as the relationship between time and light. Measurements made by Vesto, Slipher showed redshifted, or the change in light blues, evolved outside of our solar system's perspective in the elliptical and spiral nebulae that have since been identified as galaxies. The existence of these galaxies was indicated by their rapidly moving away from us at high speeds. Alongside Edwin Hubble, similar types were identified by Milton Humason, similar to the variable stars discovered by Henrietta Leavitt in elliptical and spiral forms. This allowed them to measure the nebula in relation to these galaxies and confirmed that they were higher than our own. Together with other data, the findings led to the idea that the universe is growing. If the universe grows, it suggests space expands over time, resulting in the matter it contains becoming less dense. Radiation, like light waves, diminishes as space expands, not only concentrated but also with long stretches. If we rewind the universe, it would begin to cool, and the clock the other way around would be relevant. Earlier radiation in the universe, when the universe was still young, was hotter and denser. When we rewind further, all radiation and matter would have been constrained to a smaller area, increasing the universe's density. The light that stretched as a result of cosmic expansion would, when time is reversed, have resulted in a wavelength that is shorter. If you envision higher temperatures extending back as far as physics will allow, you'd arrive at a single state where all radiation and matter existed within only one point, with infinite density and temperature. The initial concept of the Big Bang theory was formed. 5 essential expectations for the hot and dense early universe conditions resulted in the underlying theory of the Big Bang. The universe ought to exhibit expansion because of a distinct redshift relationship between the extragalactic objects. The universe ought to be relatively uniform, with star-like structures, galaxies, and galaxies clusters gradual. The middle of the 1960s, when the creation of the cosmic microwave background was discovered, provided supporting evidence for the Big Bang theory. During the 1960s, the hot Big Bang theory grew, and in the 1970s, a few difficulties emerged that the Big Bang on its own was unable to resolve. A few observations went against the notion of where the universe came from, a single condition of extremely high density and temperatures. 3 of these obstacles stand out. The first is the horizon issue. When we observe divergent directions, the universe appears to have uniform density and temperatures throughout. However, since the beginning of the region's blazing fast Big Bang, they never had the chance to transfer information or attain thermal harmony with one another. As a result, the query arises, how did they develop to maintain a consistent temperature and conditions? The second is the flatness challenge. In an expanding universe, there is a constant struggle between the forces pushing things apart during the initial expansion and the efforts of gravitational forces to impressively pull everything back together. These opposing forces in our universe appear to be in perfect harmony, resulting in a flat universe in space. The inquiry becomes, why did our universe become a reality with these specific features? The third is the monopole problem, or the problem of ancient relics. If the universe endured high temperatures and energy conditions in its infancy, why don't we see exotic leftovers like right-handed neutrinos and theoretical magnetic monopoles? It should be possible to find these particles still in existence today. As opposed to just considering these circumstances as the universe emerged, scientists, using the scientific method, tried to find a system that would organize and establish these initial conditions. Alan Guth brought about an answer to these astronomical mysteries. He published a groundbreaking paper in 1980, suggesting that a preliminary period of rapid and ongoing expansion in areas where the energy of the universe did not spread across matter and particles from radiation, but was a fundamental component of space itself through a field or a different method, could solve all 3 concerns. The horizon problem, related to temperature uniformity and the overall density of the universe, is a result of everything's interconnectedness in the past. This connection deteriorated in the beginning. Inflation, the phase of expansion, resulted in the current state of affairs observed. In relation to the flatness issue, the universe grew, so much due to inflation that in spite of its initial state, the visible portion now appears uniformly flat. Concerning the monopole issue, the absence of ancient relics is explained by inflation, which prevents the universe from reaching energies or temperatures that are too high. The highest possible temperature reached in the absence of inflation would allow the emergence of these relics. In the 1980s, accurate inflation theory and predictable predictions regarding the beginnings of the cosmic structure, which ought to be observable in the cosmic microwave background, as well as the extensive layout of the universe, were confirmed by observations dating back to the 1990s to the present day. These encompass a nearly, although not completely, scale-independent spectrum of imperfections, such as differences in density and anomalies in temperature, that are completely adiabatic and in no way isocurvature, essentially changes on scales, larger than a signal traveling at the speed of light. The expanding universe may result in a limit on the maximum temperature for the universe, particularly during the hot Big Bang, smaller than the Planck scale. Inflation is the rapid increase of space, rather than reaching a singularity, similar to the initial model for the Big Bang. Because it offers an alternative instead of a depiction of the beginning, space and time gradually emerge from a single state, inflation. This suggests an expansion that culminated in the Big Bang. This raises a fundamental concern regarding the actual start of the universe, assuming such a concept even makes sense. In the structure of the blazing Big Bang without inflation, it could be traced back to a single state in which the entire universe's size is close to zero in a limited space.